Assalamu alaikum. Welcome everybody to the second part of statistical test for chemical analysis. Today we'll have estimation and expression of measured data, T and Z test and Q test. So here we have estimation of measured values. If you have measured a lot of samples and you have replicates of your measured data, so we have two main parameters, trueness and precision. This tell you how much your sample is accurate, okay, and the level of uncertainty. So if you have suppose that the red circle is the true and correct value. So if you repeat your sample several times and you have values are scattered points away from the center, then your sample doesn't have any trueness or any precision. But if your sample around the center, but they are a little bit scattered, so you have an error between the center and the data, then you have trueness, but you still have your sample lack of precision. If your samples are close to each other, okay, but they are far away from the correct value, then you have your analysis is precise, but it's not true. If you have both correct, true, and precision of sample, then you can tell your sample is accurate and you have decreasing uncertainty. Okay, so how to determine the trueness? We have two ways to determine the trueness. It's recovery and bias. For precision, we have a lot of data to represent the precision. That means the range, the difference between the maximum value and minimum value, deviation, variance, and standard deviation. For trueness, we have recovery. Recovery is simply the value of measured data over the true value. For example, if you want to check the trueness of method of or equipment, for example, so you can get like a standard 100 ppm, for example, or 100% based on your analysis and check. So if the 100% gives you 90%, that means your recovery is 90%. Okay, the bias is a method to measure the systematic deviation from the truth, okay, or the size of error. So it's mainly for equipment, to measure the equipment, not for hand error. It's mainly for equipment error. So it's represent, you can do it by x measured minus x true over x true. For precision, we have a different method. Okay, range is the least common used, and sample or the standard deviation is the most common used. So range is x maximum minus x minimum. Then deviation, you take the average or mean of your repeated samples and check each one how much is deviated from the center or from the mean. And we also have a mean deviation. So this is the average. We make summation of all deviation and divided by their number. And coefficient of determination, this is for your trend line. It's mainly not for duplicate or replicate samples. It's used for trend line, I mean for calibration curve. Okay, we also have variance or standard deviation. Okay, variance and standard deviation. So, standard deviation. Here, I want to tell you that there is a difference between sample and population, but we will indicate the difference between them later. But the sample is for certain number of samples of population, but the population is the total number of the sample. So it's called population. So there's invariance of sample, it will be n-1. For the sample standard deviation, it will be n-1. But if it is population, okay, population, so it will be just n. And so later I will indicate the difference between sample and population. Okay. Now, how to apply statistical quality control. Suppose that you have you are working in a plant, okay, and this plant produce 500 patches of pigment per week, okay, and for each patch you have some bad patches, okay. This is bad patches. So in the plant assurance quality control, if the patch doesn't pass the color test, so it is rejected and sent back for reformulation. So now the company policy is to stop the whole process of operation if the number of bad patches produced in a week is more than 3 standard deviation above the mean value for the base period. Okay. Uh, how many bad batches in a week would it take to shut down the process? So suppose that we here have the table. This is the number of weeks, and this is number of bad patches returned for reformation. Now we want to make a process to make sure that if the number that's the I have a problem in my process and I should shut down the process and make maintenance for the production line. So now we choose the number shouldn't exceed 3 standard deviation above the mean value. And why we choose this number, I will tell you later. Okay, now let's make the statistical calculation. We have X and we have Y here. So according to these values, N is 12. The average is 18, or mean is 19.92, and we have standard deviation is 2.81. So if I apply the equation, mean plus 3 standard deviation, it will be 19.9 plus 3 times 2.8, so it will give me 28.3. So this will be the maximum number. What does it mean? That means if 29 or more bad batches are produced per week, then the process must be shut down for maintenance. The question is, why does the factory has chosen 3 standard deviation above the mean value? So now I will tell you why. First, let's say something. We have number of bad batches per week. So this is a mean. We can say this is a mean. This line represents the mean. Okay. And we have bad batches around this mean. Okay. According to the statistics, if this distribution are normal, okay, then we about 68% of the samples are distributed around one standard deviation above the mean. Okay. If okay, then 95% of the samples are distributed around the mean by 2 standard deviation, and 99.7, this is almost 100%, okay, of samples are distributed around the mean by 3 standard deviation. That's why the plant or the factory should 3 standard deviation above the mean, because it represents almost the whole distribution. Any number beyond this value means that this number is not normal. Okay. So here, let's represent this curve here. So this, if I have plus or minus, okay, according to the statistics, they said if I have a mean, okay, if I have mean, so we 38% of the samples are distributed plus or minus the mean by one standard deviation, and 95 of the samples, okay, are distributed plus or minus okay, two standard deviation, and 99.7 are distributed around the mean by 3 standard deviation plus or minus. So now we distributed the samples like this. Suppose this we have a mean, okay, and we have this is one minus standard deviation. We have two standard deviation, three standard deviation. So standard deviation here is 20. Okay, so here also we have one standard deviation plus, two standard deviation plus, and three standard deviation plus. Now the statistical people, okay, or the statistics wants to make standardized for this curve to use it for any application. Okay, so as you can see, this is normal distribution for my case. Okay, but I want to make this normal curve to be standardized, to be used for any application. So I want to remove all this number and make it only 0 plus 1 plus 2 plus 3. Okay, so now we said, for example, here we have this value is one standard deviation plus, okay, one standard deviation plus the average. So in order to standardize it, I have to minimize or cancel the mean plus dividing, and then divide this value over the standard deviation. Okay, so now if I have this value, for example represent the mean plus standard deviation, so then remove the mean, okay, remove the mean and divide it by standard deviation, so it should be 1. For example, for this value here, it's mean plus 2 standard deviation. So if I removed the mean and divided by standard deviation, then it should be 2, and so on. If I go for negative way, it will give me minus 1, minus 2, and minus 3. Okay. So now we said the location of my sample here, okay, the location of my sample here at 1. Okay, now suppose that you want to put your sample in any different position. That means I can put it here. So we said this is 1, this is 2, okay, and here is 3. Oh, it's minus 1, minus 1, minus 2, and minus 3. Suppose that you want to locate your sample in any place here or here, any place. Okay, so that means here maybe represent, for example, 1.3. 1.2. So this is called Z. Okay, so Z has different values of standard deviation above and below the okay. So now we how to represent this one in terms of Z. Now we said before we said we take this equation, we'll use this equation. So here x plus s plus or minus mean, okay, divided by standard deviation, it should be equal to z, whatever, 1, 2, 3. Okay, so now x average or mean plus standard deviation, this two together means the location of my sample in the normal curve. Okay, so I can make it, rewrite this equation in terms of x plus or minus mean divided by standard deviation equal to z. Okay, so then I can rearrange this equation. X equal to average plus or minus z times s, standard deviation, where x is the value at certain confidence level. What's mean by confidence level? That means, as we said here, we said this is 68 confidence level. Okay, this is here we said 95 confidence level. Okay, but if you have, for example, here in this part, it may be 50% confidence level. Here it may be, for example, we can say 87 or 89. confidence level. So it depends on the location of your sample. Okay. Now let's back to this part. We said the difference between population and sample. Let me give you this example. If, for example, if you want to measure, if you have graduate students, you have, for example, we can say 500 graduate students, okay? And you want to make survey for these graduate students who already employed and who still with no job, okay? So if you make calculation for all students, so if all the 50 students for your graduate students have participated in the survey, so this is called population, okay? Then the average, you have the average or mean, and you have the standard deviation. But suppose that not all students responded to your survey, and only, we can say, 100 only from 50 who respond. Okay, then now you can't assure that this 100%, this 100 represent the population, but it is just a sample. Okay, so in this case, the intervals confidence become, we have uncertainty, wider range of uncertainty. Okay, so for example, if you make distribution plus average plus or minus 1, maybe for sample, because you still have some mistake, so it should be larger. That's why we use another different, we use n minus 1. Okay, so the sample standard deviation is larger than the population standard deviation. We divided here in less number, so here we get a wider range of standard deviation. Okay, so this is the difference. So in population we usually use z, and for sample we use t, but I will explain later the difference between them. Okay, so now z-test, we said, as we said here, we have as 0 is the mean. Okay, and we have standard deviation, second standard deviation, third standard deviation, and we can go back to minus standard deviation, minus 2 standard deviation, and minus 3 standard deviation. Okay, again, and we said at the first standard deviation we have here 68 of my samples are here. Here we have 95, and here we have 99.7 confidence. Okay, so then we can say the intervals, the confidence interval around the mean, so it's equal mean plus or minus z times standard deviation. Okay, so for example, if z is 1, okay, then my intervals confidence interval are 68. If z are 2, then the interval confidence are 95. If 3, then 99.7. Okay, this is the confidence interval. Now, if you repeat your sample, okay, and as you know, when you have more replicate or for your sample analysis, that means you have more information or awareness about your analysis. That's why number of samples should be contribute to the intervals. Okay, confidence interval. That's why, okay, the better estimation become divided this value by root of n, because again, because as you have more samples or more information about your survey or analysis, then you have a better values. You have less, here we have less confidence. Okay, you have less uncertainty or more confidence. Okay, so you have less uncertainty or more confidence. Okay, so now if, for example, if you repeated your sample 3 times, so 3, so this value will become, this value together will become a larger value. Okay, but if you replicate, you have 10 replicates, then this value divided by 10. So this value will become less, and you have less value of uncertainty and more confidence. Okay, got it? Now, now I want to show you how to use the test tables. Okay, so suppose that you have area. This part is not related mainly for analytical chemistry, or but it's related to more statistical. So it's important because you can use it in reverse way for analysis. Okay, so now suppose that you have this curve, and this area that's in blue color, you want to find the area beyond this curve, below or behind this curve. Okay, so now we have z here is 1.54, and we have the here is minus 214. Okay, now just for your information, if we have area here, area, okay, is 100%. So here we have 50% of the area, and here we have 50% of the area. Okay, so for example, if we have when we said 80%, that means you have here 40%, and here we have 40%, plus or minus. We always say plus or minus. Okay, so now in z-test always come like this. Okay, it's measure the it measures the whole area from left point until this point. Okay, whole area. Okay, so now I want to measure the area behind this one. So now you still have area here. Okay, this is not can't be read. Okay, or it's not read, or you can't read it, or it's not countable. Okay, so so we have two ways to represent this area. So we can I will show you the two different ways. Okay, let's start with the easiest one. Okay, so now, as we said, this area here is 0.5, and here is 0.5. Okay, so now we can divide our shape into two areas, in the right area and left area. Okay, so for the right area, okay, now in the z-test it measures the whole area, okay, or the left included the part 1. So now we said 1.54. So let's go for 1.5. Okay, then let's go for 0.04. Okay, that means I have 1.54. So how is by the intersection we have the area is here 0.9382. Okay, so this is the whole area, but what we needed currently, we need only this part 1. So I will calculate this part 1, the right hand part area alone, and then we'll calculate the left hand area alone. So for the right hand, okay, it's become, I have to minus 0.5. So my right hand area is 0.4382. Okay, so keep this as a note on your we have the right hand area is 0.4382. Then let's go for the left side. Okay, for the left side, when I calculated the left side, I want to minus 2.14. So go for minus 214. Okay, then the area is 0.0165. But this area is only for this part, for the left part. Okay, but what I need the whole area of the left except this part. So the whole area represent what? The whole area here, whole area represent 50%, 0.5. So I can cut this area. This area represents 0.05, so minus 0.0165. So the area on the left side is 0.4838. So now I have the area of the right side, area of the left side. Then by combining them, so the area should be 0.922. Okay, then area represent 92.2. We can calculate it by a different way. So we can say this is method 1. Method 2, okay, we can calculate the whole area, okay, then remove this area alone. Okay, so for example, this whole area, okay, including all area, is 0.938. Okay, so let's write it down, 0.9382. Okay, then so this represents what? Represents the whole area. So I can cut this area alone. Okay, so this area represents 0.0165. So minus 0.0165. Okay, I'm using my calculator. Equal. So the equal is 0.822. Okay. So by this, I have the same, I calculated the area behind or below the curve. Okay. So this is how to use the test. Okay. Now for confidence level, okay, for confidence level, okay, confidence level means the area plus or minus the curve. Okay, for 50%, this means I have 25% on the right, 25% on the left. Okay, for 68, that means I have 34 on the right and 34 on the left. Okay, so in most analysis, okay, we have these values. Okay, this is a common use, and each one represent its point, its relative z. Okay, if you remember, we said 99.7 is 3 standard deviation. Okay, so z here is the standard deviation. Okay, what else? 68, it's 1. Okay, 95, okay, so it's 2. So this is the confidence level. Okay, now let's apply this model now. So in this, take an example, if we have 7 samples and the mean of these 7 samples are 1108, and the sample standard deviation is a good estimate of the population standard deviation and equal 18. Okay, calculate the confidence intervals at 80 and 95%. So why the question said here the sample standard deviation is a good estimate? That means sample, I took sample, okay, this sample not the whole sample, but it's also you can say good estimate because your sample, your analyses are homogeneous. Okay, suppose that you take water sample from the ocean, and you select one point from the ocean, from the center of the ocean. So you are confident that this sample represent are homogeneous and to represent the good estimate of the population. Okay, so hence you can use you should mention why in order to use the z-test, because if your standard deviation sample standard deviation is not a good estimate of population, like for example you are doing analysis for some environmental sample, and this environmental sample are not a good estimate, you select some sample but you didn't get the total sample and you have a variation in the sample. Okay, so then you can't say this is a good estimate, and hence you have to use t test instead of z test. I will show it to you soon. Okay, okay, now we can apply here. Okay, so we need confidence level, confidence interval at 80%. At 80%, I know the from z table 80%. 1.28. Okay, so 1.28. So I have here the mean. Okay, I have the standard deviation times the sorry, this is z value. I'm sorry, this is z value times standard deviation divided by root number of sample 7. So it gives me a 1000. This is the average plus or minus 9.2. For more confidence, you have a wider range. Okay, for more confidence, you have wider range. So we apply the same. So 95%, 95% is 1.96. So here it is 14.1. Okay. Now suppose that you submit your analysis to your client, but he wants his analysis at confidence intervals at 95%. However, he's not happy about this standard deviation, about this uncertainty. He informed you that no, this uncertainty is not doesn't meet my expectation, and I need a less uncertainty. Okay, in order to have less uncertainty, you may choose to go for another technique that give you more precise analysis. I mean more or less standard deviation. Okay, but suppose that your analysis can do this. So or suppose that you don't have the facility to go for better analysis so far. So the only way you can change this value by increasing n. So as we said, we can just value by different ways, by reducing z. Okay, so go for less confidence, or by improving standard deviation, by choose better analysis technique, or by increasing the number of n. Since the request of your client he decided certain confidence interval, and since you can change your technique, so the only way is to develop by have more analysis. Okay, now the your client said that I'm not happy about this uncertainty, and I need it to be equal only 10. Okay, then what does it mean? That means you need this value become 10. So we can apply, we can make easy equation. Okay, since we can say 10 equal z times standard deviation divided by n. So n is unknown for me. By changing the equation, by then we can get n equal 13.8. That means if you measured 14 replicates, okay, 14 replicates per sample, then this interval will be plus or minus 10 or maybe less. Okay. Now, if your standard deviation, sample standard deviation, you calculate your standard deviation, but suppose that it's not good estimate for population. Okay, for example, you select sample among the population, but this sample doesn't represent the whole. Okay, because there's a big variety in the whole. Then you have a larger or wider uncertainty. Okay, so your confidence become less. So in this case, we also have another option. If your sample is less than 30 and population standard deviation is unknown. Okay, so in this case also we use t-test. Okay, so now t-test is similar, exactly the same equation of z-test, but the only difference here, we use t instead of z because it's not normal distribution. Actually, t distribution, if we say this is normal distribution, okay, t distribution might be wider than normal distribution. Okay, so t-test here we have degree of freedom, and we have here level of uncertainty. Okay, sorry, level of confidence. Okay, so and here's degree of freedom. What is degree of freedom? Degree of freedom is number of sample minus 1. Okay, so for example, you have tested 7 samples. Okay, then your degree of freedom will be here 6. Okay, so based on what intervals you want, okay, you can choose. For example, for 80, then you can choose 1.44. For 85, then 2.45, and so on. Okay. Okay, let's take the same example we did before, but in here the sample standard deviation, we didn't say it's good estimate for the population standard deviation, so you can't use z-test, you have to use t-test. So now you can see the difference become bigger. Okay, here we said it was 9.2 and 14.4, but here it's 10.35 and 17.59. Okay, so as you can see, the uncertainty become bigger. Okay, so now let's go for another test. It's known as Q test, okay, or Dixon test. So what is Dixon test? Dixon test is simply used to identify and reject of outliers. If you have a set of samples and you want to reject, you want to decide can you reject it or not, so you can use Q test. So to apply Q-test for bad data, okay, first you have to arrange the data in order of increasing values. Okay, then calculate the Q-test. So what is Q-test? Here, uh, X test. Okay, X. This is the value you want to test it. Okay, then minus the closest value to it and divided by the maximum value and minimum value. Okay, so then compare the Q test with Q table. So this is Q table and this is the confidence level. This is the significant level. Okay, and this is alpha. Okay, so always the significance is the remaining part of the confidence. Okay, so SL measure your uncertainty, so CL or confidence interval measure your confidence, while significance level measure your uncertainty. Okay, so now here you can check the number of samples. Three. Of course, this is part of table, but you can find the Q-test tables. It's already available on the internet. Here's, for example, we have 3 samples, 4 samples, and so on. Okay, so now, okay, that's fine. So now let's take an example. So the rule is if your q test is larger than q table, okay. For example, if you calculated your q test and then you found it larger than q table, then your sample should be rejected. Okay, but if less than the assigned value in the q table, then it is accepted. Okay, so this is the rules. Okay, if q test larger than q table, then reject the questionable point. So and this is also important that only one point may be rejected from the data of using q test. Okay, so now suppose that you have this data. How many data? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10. Okay, and suppose that you want to check this value. Okay, you found that this value is very small compared with other values. Okay, and you want to check it. So first, let's arrange the in increasing order. Okay, so we point 1.6, 0.167, 0.177, and so on, from the smaller to the larger. Okay, so now Q, we said we put the test value, okay, minus the next value, okay, overall the biggest minus the smallest, okay, then it gives me 0.455. Okay, now I want to check. So now we said the number is 10. Okay, then we want to check at 90 and 95. So at 90 in the table it's 0.412, and in 95 is 0.466. Okay, now our value is 0.455. This value is larger than this value, so the number of 0.167 is it's considered outlier in or at 90% confidence. Okay, but at the wider range, 95% confidence, it less than this value, so it's not outliers. Okay, so I hope you had enjoyed this part, and see you inshallah in other parts. Thank you so much. Assalamu alaikum wa rahmatullah.